Yeah, the James Webb Telescope spotted it just outside of our solar system.
Floating more than 1,000,000 miles from Earth at the second Lagrange point, the James Webb Space Telescope has delivered its most staggering discovery to date, one that defies our most deeply held assumptions about the cosmos. The revelation is not only puzzling astronomers, but may also rewrite fundamental aspects of physics and cosmology. While the Webb telescope was designed to peer deeper into space and further back in time than any previous observatory, what it recently uncovered wasn't merely unexpected, it was once thought to be impossible. Before we start, hit the like and subscribe buttons for more exclusive news. The discovery emerged from a deep field survey conducted over several weeks, during which Webb trained its powerful near-infrared instruments on a seemingly quiet patch of sky. Nestled among the countless galaxies and ancient light signatures that populate the infant universe, the telescope captured the image of a gargantuan structure, a mature, well-formed galaxy cluster that dates back to just 500 million years after the Big Bang. By all existing models of cosmic evolution, such an entity should not exist. The early universe was presumed to be chaotic and underdeveloped, with galaxies in their infancy slowly forming through gravitational aggregation. Yet here stood a cosmic behemoth, a cluster of galaxies, dense, organized, and radiating with old stars, existing impossibly early in the timeline of the universe. This discovery challenges the standard model of cosmology, particularly the LCDM, Lambda Cold Dark Matter model, which has long governed our understanding of how the universe evolved. According to this framework, structures of such scale require billions of years to form. The gravitational pull needed to bring together that many galaxies, let alone allow them to settle into a coherent cluster, should have taken eons. Webb's data, however, tells a different story, one that paints the early universe as far more dynamic and complex than previously assumed. What makes this revelation even more astonishing is the spectral data collected by Webb's instruments. These readings show an abundance of heavy elements, what astronomers refer to as metals, within the cluster's galaxies. In theory, the first generation of stars, known as population 3 stars, were composed almost entirely of hydrogen and helium, with heavier elements forming only later through stellar fusion and supernovae. For this galaxy cluster to be so metal-rich implies that multiple generations of stars had already lived and died within just a few 100 million years of the Big Bang. It suggests a hyper-accelerated pace of stellar evolution that cannot be explained by current astrophysical models. To understand how this is even remotely possible, researchers dove into the telescope's high-resolution imaging and deep spectroscopic data. The gravitational lensing effects observed around the cluster provided critical insight into its mass and composition. It wasn't a mirage or data anomaly. This was a real massive structure with an extraordinary density and gravitational influence. The galaxies within the cluster were not haphazardly arranged, but rather showed signs of rotational dynamics, ordered star populations, and in some cases, supermassive black holes already anchored at their centers. The formation of such black holes, another long-standing astrophysical puzzle, was also believed to be a slow, cumulative process. Here they were, present and active, glowing with X-ray emissions that pierce the early cosmos. The implications of this finding are staggering. If such complexity and mass could form so early, the foundational timeline of cosmic history may be flawed. Scientists are now revisiting ideas that had once been set aside, including alternative theories of dark matter behavior, modified gravity, and even the possibility of pre-Big Bang phenomena that seeded advanced structure formation. The notion that the universe began in a simple homogeneous state is now up for debate. Some theorists have even speculated whether inflationary models, those that describe a brief exponential expansion just after the Big Bang, need dramatic revision or replacement altogether. There's also the curious issue of entropy. The thermodynamic arrow of time implies that the universe began in a state of extremely low entropy and has been evolving toward disorder ever since. But a highly structured, high-density galaxy cluster so early in cosmic history could suggest that entropy was not as minimal as previously believed. This could indicate a more complex initial state of the universe, one that doesn't align with the clean simplicity outlined by the standard Big Bang model. The implications stretch beyond astrophysics into the very laws that govern the arrow of time and the fabric of reality. Even the process of star formation itself is under new scrutiny. Current understanding holds that stars form within molecular clouds over relatively long timescales, collapsing under their own gravity and eventually igniting fusion at their cores. But the speed at which these early galaxies formed stars, let alone hosted mature stellar populations, suggests either vastly different initial conditions or a fundamental misunderstanding of the mechanics involved. Could there be unknown processes that allow star formation to leap forward under certain extreme conditions? Could dark matter play a more active role in this dynamic than previously believed? This impossible discovery has also rekindled interest in exotic forms of matter and energy. If standard baryonic matter and cold dark matter can't account for such early structure, then perhaps there's another form of energy, something faster acting, more gravitationally potent, that help bind matter together in the young cosmos. Concepts like warm dark matter, fuzzy dark matter, or even primordial black holes have now surged back into the realm of serious scientific inquiry. Each presents a different solution to the riddle, but all carry radical consequences for the theories that have, until now, elegantly explained the cosmos. And then there's the question of time itself. The timeline of the early universe, as inferred from redshift measurements, is deeply rooted in the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. But what if that assumption is flawed? What if our cosmic vantage point is skewed, giving us a false reading of the universe's age or rate of expansion in its infancy? Some researchers are now contemplating whether the early universe experienced phases of localized acceleration or turbulence, zones where time passed differently or gravity operated under anomalous conditions. These ideas were once considered fringe, but Webb's discovery lends them newfound credibility. The implications extend even into the realm of quantum gravity and string theory. If the early universe hosted highly structured, high-mass entities at a time when space-time was still in its formative stages, then the interplay between gravity and quantum mechanics may have been far more intricate than previously conceived. Some physicists are now toying with the notion that space-time itself may have crystallized out of a more chaotic quantum foam in non-uniform ways, leading to pockets of accelerated structure formation. This challenges the smooth curvature assumed by general relativity and may hint at deeper, undiscovered laws at the Planck scale. Beyond its theoretical ramifications, this discovery also demonstrates the sheer power and precision of the James Webb Space Telescope. Its ability to resolve light from billions of years ago, to pierce through cosmic dust and measure the elemental composition of ancient galaxies, is revolutionizing observational astronomy. What once lay hidden in the mists of the cosmic dawn is now illuminated with unprecedented clarity. And with each image Webb returns, humanity moves closer to understanding not just where the universe came from, but why it looks the way it does. This impossible galaxy cluster is not an isolated case either. Preliminary analyses of adjacent regions in the same deep field image suggest there may be more such structures scattered across the early cosmos. If confirmed, this would not merely be a curiosity, it would be a pattern, a signature of cosmic behavior fundamentally different from what was expected. Such a revelation would imply that the entire early universe was a more fertile, more active environment for structure formation than standard models allow. The consequences would ripple through every corner of astrophysics, cosmology, and even philosophical conceptions of time and causality. The profound beauty of this moment lies not only in the discovery itself, but in the questions it raises. For decades, scientists have refined their models, working with the best data available. Now that data has improved exponentially, and with it comes the need to challenge the very foundations on which modern cosmology is built. It's a thrilling, unsettling, and awe-inspiring moment for science. The cosmos, once thought to be gradually unfolding according to well-understood principles, may be telling a different story, one of unexpected complexity and untamed dynamism from its very beginning. The idea that galaxies could coalesce and evolve so swiftly opens new doors to our understanding of time's flow in the cosmos. It invites comparisons to early myths and metaphysical questions about creation, how structure, order, and complexity can emerge from chaos. That these questions are now grounded in observable data from a real object seen with real instruments gives them a scientific legitimacy previously lacking. Webb's telescope has become a time machine not just to the past, but to a past that never looked the way we thought it did. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on James Webb's discovery? What do you think it revealed? We want to hear from you. Thank you for watching and see you next time.